Hello students, uh, today we are starting a new topic, that is induced current and induced charge. Now in the previous class I have told you that with the change of EMF, suppose over here is a magnet with north pole. If you pull it back and forth, if you push it back and forth, then the magnetic flux over here will change. The magnetic flux or the magnetic field coming out of this will change. So with the change in magnetic flux, an EMF will be introduced in this coil. So the amount of EMF introduced in the coil is given by Faraday's law, that is E is equals to change in magnetic flux per time. Okay, so if the number of coils over here is N, capital N, then your EMF becomes minus N del phi B divided by del T. So this will be the amount of EMF that is being generated with the change of magnetic flux. Now suppose if this coil has got a resistance or the total resistance capital R, then the current or the induced current which is being generated is E by R. E is the EMF divided by the resistance. Now if you put the value of EMF over here, then I becomes, we are just ignoring the negative sign, so I becomes N del phi B by del T divided by R, or we can write it R over here. So this is the amount of induced current in the circuit. Now what next we have to find is the induced charge. Induced charge, for that the charge flowing per unit time Q is I into del T. This is from the same equation, that is I is equals to Q by T. So now in the place of I we are putting this value, that is N by R del phi B by del T into del T. Del T gets cancelled, so ultimately your charge becomes N by R del phi B. Okay, so this is the induced charge which is being generated with the change of magnetic flux. Now the unit of charge is coulomb. The number of turns doesn't have unit. The unit of magnetic flux is Weber and resistance is ohm. So from this equation what we have seen is charge is time independent. So number of charge or the change in magnetic flux may be rapid or slow, the charge in the current will still remain the same. So however fast we move the magnet, the number of charge will remain the same. So this is the value of charge and this is the value of current. So with that we move on to the next topic, which is kind of a continuation. Motion of a straight conductor in a uniform magnetic field, or motional EMF. That is, we have uniform magnetic field. All this cross over here is a sign of uniform magnetic field. Now the magnetic field is directed inward, okay, perpendicular to this page. So if magnetic field is directed inward, all the sign that is cross will resemble it. If it is a dot, then it directs outward. So there is uniform magnetic field, that is denoted by B. Now we take our rod or a straight conductor whose length is L. Okay, the length of the conductor is L and the conductor is moving with velocity V towards the right. The conductor is J, represented by J and K. So JK is a conductor of length L moving towards the right in a uniform magnetic field. Now next, we know that there are always some free electrons in a conductor. The atoms from which these electrons are detached have excess of positive charge. Thus, the conductor has some positive and some negative charges. Of these, only the negative charges can move about within the conductor. So there are positive and negative charges. Only the negative charges will be about to move because these are electrons. Positive charges are the atoms or the protons which will not be able to move. With the conducting rod moving with velocity v, this positive and negative charges also move in the magnetic field B towards right along with the rod. So this also moves along with the rod. We have read that when a charge Q moves in a magnetic field B with a velocity v perpendicular to the field, it is acted upon by a magnetic force Fm. Okay, there will be a magnetic force Fm, which is QV. B. Q is charge, V is velocity, B is magnetic field strength. The force Fm is also known as Lorentz force, and its direction according to the Fleming's left-hand rule is the force Fm on positive charge will be towards this side, towards J, and for negative charge will be towards K. Okay, this is according to Fleming's left-hand rule. Since only the electrons are free to move within the rod, they start moving towards the end K of the rod. With the influence of this force, electron moves towards K. Then there will become a differential of electron near this rod, that is, near this end, that is J. And this end becomes positively charged. Simultaneously, there will be an excess of electrons at the end K, and this becomes negatively charged. So J becomes positively charged, this side K becomes negatively charged. Hence an electric potential difference V will be induced. You know that electric potential, when there is a difference of charge, there will be electric potential introduced, that is V. And with the presence of electric potential, there will be electric field created. So electric field E will be created, which will be equals to V by L. V is the electric potential per charge. E is the electric field. Now the direction of electric field. Let this equation be equation number 1. Now the direction of electric field. The direction of E is from positive to negative charge, that is from J to K. Direction is from J to K. The field E imposes an electric force Fe on each charge. So with electric charge, there comes electric force, that is Fe. The magnitude of Fe, the force is Q into E. Okay, this will be the amount of electric force. The direction of the electric force on the positive charge will be towards K. Okay, for this one, it will be from positive to negative. So the force will be from positive charge to the negative charge. So electric force will be towards negative charge. And for the negative charge, okay, or for the electron, the direction of force will be towards the positive charge. So the direction of force for this one will be towards positive charge. So the force Fe is opposite, also Fm is also opposite. As more and more electron reaches the end K, the magnitude of electric force Fe goes on increasing until it equals Fm. So when Fm and Fe will be equal on each charge, there will be the resultant force on each charge on the rod will become 0, and the movement of the electron towards K stops. So when Fe becomes equals to Fm, then the movement of electron will stop. So Fe was Q into E, Fm is QVB. QQ gets cancelled. What we get is E is equals to V into B, or V is equals to, this is equation number 2. Now from equation 1 and 2. From equation 1 and 2, what we can write is V by L is equals to V into B. This is B into V. This V is velocity, this V is electric potential. Please do not get confused. So from here, V is equals to B V L. So this is the amount of electric potential which is being generated when a charged conductor moves in a uniform magnetic field with velocity V. The unit of electric potential will be volt. Magnetic field will be Weber per meter square. Velocity will be meter per second and length will be meter. So this is also known as motional EMF. So this derivation was to determine the motional EMF or the electromotive force when a charged conductor is moving on a uniform magnetic field. So today we have discussed two topics, that is induced charge and motional EMF.